Okay, let us look at this problem. We're working in the probability space minus a half-half together with the Borel sets on this interval, and on this interval Lebesgue measure M is a probability measure. And what I'm going to do is I'm going to look at the conditional expectation of a random variable x with respect to a sigma field h, where x is defined in this way. This is the indicator function of the interval 0,5, and h is a sigma field that consists of all sets that can be written in the following way. A set A in the sigma field is either a Borel subset of the interval 0,5, so if we draw a line here, then A is going to be either a Borel set here, which I'm going to note in this way, or A is the union of this set and the interval minus a half 0, which starts at minus a half and it goes up to 0, it doesn't include 0. Okay, now if you want to determine conditional expectation, then we need to find a random variable that satisfies two properties. The first property is that this conditional expectation has to be measurable with respect to h. Second property is that if we take any set A in the sigma field h, then the integral over to the set A of this conditional expectation with respect to our probability measure, which is h, has to be equal to the integral of the random variable that we take in the conditional expectation of with respect to our probability measure. And once we have established these two properties, then we know what the conditional expectation is almost surely up to a set of measure 1. So these two properties determine the conditional expectation uniquely for all practical purposes. Now it turns out that if we look at our random variable here, what is it? Well, it's an indicator function, which makes me very happy because indicator functions are discrete random variables, and a discrete random variable has some very nice properties. So let's write it out down here. X is equal to 1 if x is an element of the interval 0,5. It's equal to 0 if x is an element of the interval minus a half, 0. And it's very good that this set is actually mentioned explicitly here. Now, since the Borel sets also contain the empty set, if you take this union with this set and the empty set, then that set is also going to be in H, so that's really good news. So let us see. You have a discrete random variable down here. It has a partition, which is, it has two elements, minus a half and 0, a half. Now, as I've just explained, this is equal to minus a half, 0, union of the empty set. The empty set, of course, is always an element of any sigma field. And the fact that we can write it in a union like this means that it must be an element of H. With this set here, of course, if we look at the Borel set on the interval 0,5, this is exactly in there because this is one of the defining properties of a sigma field. So this is in that Borel sigma field, so the interval 0,5 is in H. So these two properties mean that every member of the partition of X is in the sigma field H, and therefore x itself is h measurable. So x itself satisfies this property A that I've written down here. These are the properties of conditional expectation. These are the properties themselves of conditional expectation. So this means that x satisfies the first property. Also, of course, if you substitute x for the expected value of x conditional h, then the left hand side is trivially equal to the right hand side, because of course x is equal to x. So x itself satisfies properties AB of conditional expectation, and therefore expected value of x given h is equal to expected value of x. Expected value of x given h is equal to x almost surely. Thank you very much.